Yeah, hello and welcome back to the PML School. Today we have our first user presentation. As you remember, some time ago I asked you the audience, to present a PML model on your own. And this really should not be viewed as an examination of what you might have learned through the PML School webinar series, but rather, I wanted to encourage you to share and exchange interesting scenarios from your own and share with a larger audience. So today it's a pleasure to introduce you to the first speaker of this series. It's Dr. Loan Pham. She's a senior pharmacokinetic scientist at Camargo Pharmaceutical Services. And there she is a scientific leader who provides strategic oversight of PK/PD projects, in which she works on the design, analysis, and interpretation of projects through various development phases. Dr. Pham earned her Doctor of Pharmacy degree from Hanoi College of Pharmacy, and she has a PhD from Oregon State University. So, Loan, welcome to this event, and I'm now handing over to you, so please go ahead and the stage is yours.
Thank you, Bernd. Hi, everyone. For this session today, we will use Phoenix to build a minimal PBPK model for monoclonal antibodies. So we are going to construct the model that was proposed by Dr. Cal group. I will start by introducing the theoretical and objectives of the model. Then I will walk you through the steps to build the Phoenix textual model, followed by a demonstration. We will have questions and answers at the end of the session. Moving forward, in short, I will call monoclonal antibodies mAbs. So in general, the approach is that when only plasma or blood data is available, we can use the major physiologic attributes from full PBPK model for a simpler approach that offers system average rather than tissue specific. But still, we can obtain parameters with more practical values. The figure on top here provides an overview of mAbs distribution. So mAbs are largely confined to plasma without distribution into the blood cells. This model uses plasma volume as initial distribution space. The mAbs can escape the vascular space by both diffusion and convection into the interstitial space and get out to lymph. Based on the published research, transcapillary escape rate is primarily driven by convective transport. So this model considers convection is the only distribution pathway. The vascular endothelial endosomes is frequently included in the full PBPK model to evaluate the FcRn salvage, but overall volume of vascular endothelial endosomes in adults is just approximately 0.4% plasma and less than 0.1% ISF volume. So regarding the mAbs distribution of the mAbs within the vascular endothelial endosomes, this model considers ISF is the only extra vascular distribution space for mAbs. This is a diagram of the minimal PBPK model. This is the artwork from the Dr. Chesco group. It has 4 distribution spaces for mAbs. We have plasma here and lymph, and 2 types of tissues in the model, tight tissues and leaky tissues. Okay, now mAbs come into plasma space and get into the tight tissue, get out to the lymph, and from lymph it will then go back to plasma. And the convective uptake from plasma space to the tight tissue equal lymph flow rate to the tight tissue L1 times the 1 minus the vascular reflection coefficient for the tight tissue, sigma 1, and similarly for the liquid tissue. The sigma 2 here is the vascular reflection coefficient for the liquid tissue. The uptake to the lymph from the tight tissue and to the liquid tissue, we demonstrated right here, and we use the sigma L. It is the lymphatic capillary reflection coefficient. Is known is 0.2 from published literature. This model also used KP. This is a fraction of the available ISF volume for mAb distribution, and is equal to 0.8. And the total ISF volume in adults is 15.6 liters. Now, all the values and relationship between parameters here are from published literature. We will go through those parameters again when we build the model. Let's see. So the objective is to fit only plasma concentration data, but we want to estimate the reflection coefficient towards the tight tissue and liquid tissue, and we want to know the clearance of the mAb, either it comes from plasma or in tissue. And we also want to simulate the mAb condition versus time profiles in plasma, liquid, and tight tissue. Now, we are going to run Model A that only have clearance happen in plasma space. Model B has clearance happen in tissue space only. And all initial conditions are concentration equals 0. So that is how the graphical model will look like in Phoenix inner interface. Those coming into plasma space, let's see, mAbs coming out to the liquid tissue, coming out to the tight. It will coming back to plasma via this one. And Model A have clearance from plasma space. Model B have clearance get out from the liquid tissue and tight tissue right here. And then we see the convection transport to the liquid tissue, convection transport to the tight tissue here. Now, let's see. This is how differential equations, I'm presenting the combined Model A and B in case, later you want to evaluate the, to see if the clearance happen both in plasma and tissue together when you have more data, not just only plasma data. And the left-hand side right here is a change of drug concentration in plasma space over time. Input here, input is the dose in amount divided by volume in plasma. We get the concentration. And then we look at the concentration that is in the coming in, or in the coming in like from lymph right here, but coming out, we need to minus the concentration coming out to the liquid tissue and plasma. So you can see coming out to the liquid tissue equal concentration at plasma times the lymph flow rate to the C tight, and times the 1 minus sigma 1. Sigma 1 is, again, is the reflection coefficient from plasma to the tight tissue. So this group is divided to the volume, so we get the concentration. And similar, you'll see the differential equation for the tight tissue, liquid tissue, and the lymph. All right, so here. So now this is how Phoenix handle differential equations. Please note that Phoenix incorporates, for the input, Phoenix incorporates this nicely via dose point statement. It makes it much easier to construct the model. We'll get to the dose input later in the demonstration. Now, note that the Phoenix is evaluating the change of drug amount over time in the drift command, and then it will convert to the concentration later by a very simple conversion. We'll see in the model, textual model later. These are publications that I used to get digitized data for the demonstration. We will use data of MEDI 528 to fit the model A and B, and then we compare the fitting between the two. Then a quick summary of the model fitting for zevokizumab and HC2 will be presented as well. So I will usually start with the built-in Phoenix model. Since our PBPK, as you see, has more than 3 compartments, so I just first, choose PK, microparameter, IV, because it has like a maximum compartment 3 compartment here. And for the residual error, just pick multiplicative to begin with. And then click Edit as Graphical. And it will bring up the graphical mode. And now from the graphical mode, we'll start adding more compartments. Name them the way we want, and then once the model is built the way we want it, we switch to edit as textual. This will provide us a very nice framework to revise the textual model while we can avoid unnecessary error that might happen if we write the model from the scratch. We will then now, so like I said, I just provide you the textual model to run both model A and B, or we can run it combined when you have more data later. So let's go through the model together. For this model, dose in microgram, volume in mil, flow rate and clearance in liter per day, time in day, remember that, and concentration is microgram per mil. So we start insert parameter relationship here. So everything that you know, you put it in here. And then I kind of have a habit to organize my code like this. So we already went through the differential equation together already. So this is for the amount of plasma, type, tissue, leaky, and lymph. Now the dose point here specifies drug input in plasma space, the first compartment. And then these are equations to convert amounts to concentration. It is very cool that we have secondary statement right here. It's optional. You can put anything you are interested in here. For this project, we are interested in knowing the transcapillary escape rate, and this is how we calculate it. You remember? So this one getting out to tight tissues, this is the one who getting out to the leaky tissue. Okay, let's go here. And then we have a block for initial estimate of the within error standard deviation right here. For this model, we are going to use multiplicative error model. These are all of the fixed effects. Parameter values are all frozen. We know we fix it. We fix them all. And then these are 3 parameters that we want to estimate. This is lower bound, initial estimate and upper bound. Let's see. Now remember, if you want to run model B, you want to estimate clearance from tissue. You want to run model A, you estimate the clearance B. I think that I missed something. Okay, here. So remember, I wanted to go back here to explain. So if you want to run model B, you would want to omit this portion because you don't want to consider the clearance out from plasma space. And if you want to run model A, then you want to omit this portion. This is the clearance from the tight tissue, and then this is the portion from the clearance portion from the liquid tissue. All right. All right, so we will go to the demonstration process. In this demonstration, we are going to use data from FORMADI 528. We have, it's in human data, we have 4 different doses, 0.3, 1, 3, 9 milligram per kilogram. This administered infusion. Infusion time depends on the dose. Sampling time points up to 48 days. And remember, the time unit in this project is days. I'm going to switch to my screen for the demonstration. Show my screen. Yeah. Are you all seeing my screen right now? Bernd?
Yeah, we can see. Yeah,
okay.
Thanks.
So I now have the metadata right here. You see the time column right here, concentration, the treatment. I use treatment dose, and then the amount, the total amount. And then look at the dose right here. So it's different treatment, different dose, and then the amount right here. Remember the duration. The duration is the time of infusion. Remember, it's days, so you need to have duration like units a day. Now, let's look at the plasma concentration profile. And it's time, it's concentration, and then, well, let's do it separate. And then, look at this here, this quick here. Easier to see and run. All right, right here, I'm going to make sure I will scale that so you can see it. Okay, I want to make it like book here. More beautiful. We have color, different color. So it may be easier to look at. So this is how the this is 4 different mean plasma concentration profiles for the 4 different doses. Okay, so then the next step, as I said, I'm going to send it to the model. Let's select PK, insert IV, 3 compartments, and let's see, we do multiplicative to begin with. What else? That's it. Oh no, I uncheck the closed form so that we can see the differential equation on the right hand. So we get, and we want to edit as graphical. Yeah. All right, move it around a little bit right here. Okay. Nice. So let's get started. Here. So let's work on plasma compartments first. We name here, I use this plasma concentration, plasma. And then from plasma, it gets to the tight tissue. Let's name it tight tissue. That's liquid tissue. The way you want it. to see. Let's look at this one. It should be one way. Yeah. And let's see, you know, just look at the code right here. It's very responsive, very cool. Clearance here is for the leaky, so I remember it is L2 times 1 minus S2. It's getting out to the leaky compartment. All right, and then let's work here. It should go to one way. Yeah, one way, getting out. So this is tight, tight, tight. Okay, and then this one is number 1 times 1 minus plus 1. Right? All right, then we know that this guy will go into the limb, so we need one compartment here. Insert. Say flow, compartment here. Then we want to insert the flow. One here. Oh no. Wrong. Insert flow. Here, go back here first. So remember from this name it's lymph. The lymph here. Lymph. Lymph. And then remember it's going back. Clearance mode, and then it's going back via the lymph flow rate to the plasma, and then these two guys going up to the lymph. So we'll add into the flow, you go here, you click here, and then we'll move it around a little bit, and then here is clearance mode, and it should be L2 and 1 minus S. Yeah, so SL is the reflection coefficient for the lymph, from the leaky to the lymph. And then here, we want to insert the flow. Here, here. And then this should be the clearance mode, and L1. 1 minus SL for the lymph. And then, you know, I want to incorporate the model B in here. So I want to insert the one compartment elimination rate right here from the leaky get out to clearance. So it should be clearance I. Yeah. Then clearance out from the tighter tube as well. The flow for it. So I noticed that I need this right here. I should name it clearance P. P. You know, just to make sure. So let's see what else that is anything that I miss here. I think we are good. Now from this mode, I will switch to edit as textual. It already gives me like a lot of information here, so we will not make any, you know, silly error if you build it from the beginning. So you edit as textual, yeah. All right. So, you know, one thing that I like about Phoenix is that I always look at the warning column window right here. It will tell me exactly, like almost every errors or anything that I don't have in my code. So I usually work through the model and then I look at this window. So let's begin it. Begin to insert what we know here, like V type. We know that it is 0.65 from the duration of the ISF, but only the available volume that is available for mAbs distribution. So you use P here, and then we do the V leaky equal. The rest of it should be for the leaky. So note that it takes the subscript very seriously. So then we know that the rate, convection rate, the lean flow rate to the tight tissue equal times the total flow rate, and then the flow rate to the okay, we have it all in here. And then look at this. This is the urine. We are not interested in the urine compartment, and then we don't have any measurement in it, so delete. This is the compartment that's getting out of the tight tissue and leaky tissue. We don't have anything, no interest, and we don't measure anything here, so delete. It is conversion to concentration in plasma, so leave it here. For the dose point, we are not interested in any of the individual in the dose, or the rate, or dose in infinity, so we delete this part. And then this conversion for the tight tissue, this is the error model. Conversion. With conversion for the lean tissue, we are not running population, so this will go out. And then this is a 65, leave it here, we'll edit it. So, and then all of the random, we are not running population PK, so this will get out. So now we'll walk through this one. We name the way we need it to be corrected for the model, and then like for example, like V tie here, we already know it in relation to the ISF. We delete it here. So I could go through the code diligently like this, and then we'll make it work until, the column, the window right here tell me no warnings. So if you keep doing it, I would like to show you the model. So when this is how the textual model will look like at the end. So like I said, we if we know the values of parameters, you freeze it, and this is a sign that we want to estimate. So you are looking at clearance I right here. That means I am looking at model B. All right. So and then if you want to run model, and then I have clearance P right here, it is model A. So I can prepare it and then copy and paste and then edit it accordingly for the model A. Only the for the model A, only the clearance P is to be estimated, and then all of the clearance portion out of tight tissue and leaky tissues out, this part, like I said. And then model B similarly. And then we hit run, and here's how the model A fits to the 4 different doses. The low dose, it's kind of going through the, this is a little underestimate, a little overestimate, a little underestimate, but this is the digital data, and this is the mean curve, and we only have 4 profiles to begin with, so I think it's good. When you run model A, let's look at the results. So I usually, let's see the data table. So model A, we are going to estimate the clearance from plasma, estimate the sigma 1 and sigma 2. So reflection coefficient for the tight tissue should be, higher than for the liquid tissue. It's more difficult to get in. So this kind of reflects this situation for the biological aspects of the model. I want to look how it fits. Let's see. So this is how the model A fits to the different doses data. Like I said, it's a little underestimate for the higher dose, and kind of going through all of the data points for the lower dose. And then similarly for the model B fitting, let's look at model B. What's the result? Let's look at the data table. So the model, what I'm looking at? Okay, yeah, model B. So clearance I. This is the estimate of the total clearance out of the tissue. Somehow this model gives us the value of the reflection coefficient for the liquid tissue higher than tight tissue. Kind of not, sensible. We are going to compare between the two model A and B. So the way we do it is we go to the overall table. We send to the data append worksheet, and then we have 2 worksheets to compare. So you go like this, and then for worksheet 2, we want to import the overall table from the model B right here, and then we want to compare them all, and then send. So these are the comparison between the 2 models, and looks like they are not very different from one another. And remember that, and then the return code here looks like the model A a little better. So based on the result for the model A, I saw that the number, the value of sigma 1 is greater than sigma 2. I kind of go with the model A. So if I go with the model A, then I want to see the model A fitting, how it fits through the data, and then I want to simulate the profile from the model A. So here's what we are going to do. If the model A is good, you do the copy right here, because we want to simulate the condition for the tight liquid tissue. I'll go here. And then in the run option, now before we go anywhere, we go to the 55 here. And we want to get all of the PK parameters value for the simulation. We say accept. Okay. Then in the run option, we want to click on simulation, predictive check, and then we going to add a table, add simulation table right here. So what we want to simulate is concentration from time 0 to 100. You know, the unit for time is days, so I want to capture the Cmax. So I kind of go small steps. And we want to simulate C in plasma, C in liquid, C in tight tissue, C in how about lymph? Let's look at lymph as well. Yeah. All right. Is there anything I need here? Run knife. Okay. How it works. So this is the raw scene table. Okay, I'm going to export it right here, Yeah. And then I want to import it in, import the data in, and we want to see it. We have the plasma, the tight, the liquid here. Okay, finish it. Okay, let's see. So remember the treatment becomes ID. So I am going to sort it. TAM, plasma, liquid, and lymph. And there are tons of data time points that we just simulate. You don't want to show markers on the profile. It's messy. So we will uncheck the markers here. Let's see. Right. How to scale that? Oh. Yeah. So this is a concentration versus time profile we wanted to generate for the this plasma, tie, the little coming in, liquid tissue, and the lymph. This is the level for the highest concentration. So I'm going to go back to the presentation right now. So let's see. So this is model fitting, and this is simulation for plasma, tight tissue, liquid tissue, and lymph. And this is I would like to show you this one because you remember when we run model A and B for the MEDI 538, it doesn't really show us if the clearance get out from plasma versus tissue. They look kind of, they can fit to the data quite nicely. So for bevacizumab, I did just the same, and for this drug, model A works much better. So if I use model A to, this is the data set that we obtained from the model A, and the reflection coefficient towards the tight tissue is higher than the liquid tissue, and this is the clearance from plasma that we estimated. So this is how the model A fit to the bevacizumab data for 5 different dose levels, and we were able to simulate the concentration for the different tissue, plasma, and lymph as well. So I wanted to show you the data from ST2. This is the data that obtained from rat, animal, not human, like other products that I just showed you. We have 4 different dose levels in here, and then model B fits a little better than model A. It kind of, not be able to capture the very low dose, a little overestimate the higher dose. It goes through some of the time points. It does not for the other time points. However, this is rat data, and we only have the mean data, and it's 4 profiles, and it's animal, so it's pretty good. And then this is where the model can be applied to, because the Dr. Chesco's group lab, they also get concentration from the liquid tissue and the tight tissue and see how the simulation fit into the data, the simulated versus observed. And I capture them right here. The simulation kind of captures the range of the concentration for the tight tissue and for the liquid tissue. So this is a trend that if you can do when you are at early phase of drug development and you don't have a lot of data. You can start with minimal PBPK model and then moving towards the full PBPK model. So I would like to conclude the session today. To me, the minimal PBPK model by count group, I think this is the artwork that includes the major distributional characteristics of mAbs, and it can serve as intermediate step when we move towards the full PBPK model for the specific products that you're working with. And this model, only from plasma, but it can, be able to estimate the mAb concentration versus sample size in 2 different tissue group, liquid and tight, and it depends. You can group them, as your preference and based on, the porous of the plasma perfusion of the tissue type. And then it can estimate the mAb clearance, and we can simulate the concentration at the tight tissue or liquid tissue. All right, I will let Bernd to continue the presentation.
Okay, yeah, thanks, Loan. Very nice presentation, very nice demonstration. We already have a couple of questions, but please feel free to post it into the Q&A console, and we might not have time to deal with all the questions, but we will upload those questions and the corresponding answers to our forum, as well as including all the materials, the Phoenix project file, the slide deck, and a link to the recorded session. Loan, we have got a couple of questions that you might want to cover now.
Yeah, so I am looking at the question right now. So the question is, why do you have A5 and A6? So as you saw when I walked through the presentation, we don't need A5 and A6. We don't need it to run the model because we are not going to measure that amount in the tight tissue, and we just want to demonstrate that the clearance is getting out of tight tissue and liquid tissue. Look, would you share slides? Yeah, we are going to share the slide deck and the Phoenix model as well, and then you can have the code. The clearance same from liquid and tight tissue. Well, we assume we have to assume that the clearance is the same between the tight tissue and liquid tissue. Let's see.
Okay. All right. I guess. Yeah.
Yeah.
Shall we? I mean, we can conclude now. Loan, we are covering the rest of the questions on our forum when we post the questions together with the answers. Maybe you can switch on, this next slide. Move to the next slide and okay. Oh, I need to do that. Oh, all right, thanks, Aaron. Yeah, maybe just for coming up, we've got 2 more sessions for this year. There's another user presentation in 2 weeks' time on November 30th. Frank Strebel from a company Morphosis will also talk about monoclonal antibodies. He wrote a textual model according to Gabrielsson that he wants to present to us. And on December 14th, I will give the final webinar session of this year with an adaptive simulation where I can show you how we can extend the Phoenix modeling language to trial simulation. So I've got a preclinical example, and I can show you how you can simulate a desired outcome. So December 14th for that. For the next year, for the coming year, we talked about this previously, but this will happen as a new longer series in 2018. So we've got a bunch of models, popular non-mem models that we've translated to PML code. So we will present these in individual sessions where we set up and run the non-mem models in Phoenix, as well as at the same time the same models in Phoenix and LME, and then we compare the results. That's coming in 2018. With that, I guess we are at the end of today's sessions. I thank everyone for attending and hope to see you next time in 2 weeks with Frank Strebel's presentation on TMDD modeling using the quasi-equilibrium assumption. With that, I want to close. Thank you all, and you may disconnect now.